This is the materials lab. In this lab, we look at the properties of materials and their various characteristics. So we may have a sample like this that we then put in a tensile machine and break and pull it until we have a failure surface. In this laboratory, we want to look at the failure surface. To do that, we're going to take the failed sample and come over to a sectioning machine where we actually cut a little piece of that sample off. We'll then put that piece on this piston in this mounting machine and allow that piston to settle down and fill the cylinder with bakelite powder. We compress and heat that powder until it fuses and then release it and jack it back out. And out of that machine, we get a mounted sample. The reason to mount the sample is we take that little piece and now we have something that's big enough that we can hang on to in our hands. We'll take the mounted sample over and put it in this polishing machine. We're able to vary the grits on the polisher. So initially, we're going to sand the material off to get a flat surface. We might start with an 80 or 60 grit. And then we will change those grits on these pads until we get down to a micron polishing surface. Our intent is to bring the surface down to a mirror finish. Once we have a mirror finish on the sample, we'll then etch the sample, which allows us to see the individual phases and the grain sizes, and we'll come over and then look at the sample under a microscope. There are two kinds of microscopes in this laboratory. The first is a stereoscope. We have digital cameras on top of the microscope so that we can project the image to a computer screen and take pictures of that image. That allows us to discuss the image with the class without having everybody have to look in the microscope. So the purpose of the stereoscope is to be able to discern depth in the sample, and so the depth of field is greater and we can see features along the failure surface of that part. If we come over to the metallurgical microscope, so in these metallurgical scopes, the depth of field is much less, and that's the reason why we need a highly polished and flat surface. This microscope has the ability to change the objectives, and we can mount 5 or 6 objectives in a carousel where the magnification ranges anywhere from 5 or 10 power up towards 100 power. In this image, these little spheres are carborundum particles and the matrix is a nickel metal. Those spheres have been suspended in that nickel, and then as we polish the surface, the carborundum spheres provide a hardened surface for that material. We're interested in the distribution of those spheres and if in the process, if any of those spheres were actually degraded or broken. So in this slide we can see that most of the spheres are still round shapes and are packed well, distributed quite well within the matrix. After we've got the sample mounted, we might also be looking or interested in looking at the hardness of the material. And so we can run a hardness test on it. In this case, we're going to run the Rockwell Hardness C scale with a diamond indenter. We put the sample under the indenter and raise the sample up until we start to apply pressure to it. We'll apply pressure until the scale goes up to the test point. And at this point, the instrument takes over and runs the hardness test for us. There's a series of weights in here that apply a specific amount of pressure to the indenter, and then the instrument measures the depth of that indentation to calculate the hardness. After we're done, we pull the sample out and report that the Rockwell Hardness C scale for the sample was 20.7. One of the other things that we do in this lab is work with strain gauges in order to determine the strain on a material. We have several experiments set up where we have mounted strain gauges on the material. These are little foil gauges that when the gauge is strained, it changes the electrical properties of the material, and we can measure this physical strain of the material that it's attached to. So we'll set these up in a cantilevered loading device and then measure the strain on these gauges. In this case, there's a gauge on the top of the beam and a gauge on the bottom, And as we apply strain, then those strains are read digitally out on the machine as this calibrated to microstrains. So we might bring this up to 200 microstrains in the top gauge, and then get a reading by reading the second gauge. So you can see those gauge readings. There's a number of these experiments that are set up that allow us to look at the bending properties and the flexure properties and the relationships between stress and strain in these materials.